I count as this is roughly about 70 students. I would gain half the class. As you saw, I will start slowly. I will start with some admin slides, especially regarding quiz 1. So those who came early, these are some information for you. There will be 5 sections, similar as last year's quiz 1. With some changes. By the way, last year's quiz 1 is... Okay, I will open Workbin to show it to you. Yesterday I have uploaded this file. This is last year's quiz 1. Right, last year's quiz 1. So we are going to use a similar format with some changes. Okay, first is we are not going to use 2 rooms. Last year we used 2 rooms. I realized that COM1 SR1 is big enough for everyone. So for this time, we will just use SR1, COM1 level 2 SR1 next in the next building. Then the timing is from 10 to 11:40, 100 minutes. I reduced the time by 20 minutes and I scaled down the difficulty level by a bit. And what else? Oh, and then the other changes is last year I have extension of PS1 and PS2 in quiz 1, but now I want to make it independent so that each quiz 1, quiz 2 are not dependent on PS1 or PS2 results. They are independent now. Right. Then I uploaded these questions, but I don't have the answers. Right. I have the answers, but I'm not going to upload it. If you want to discuss the solution, do it in discussion forum or among yourselves. These are the changes. Okay. The material will be lecture 1 to 4 last week, tutorial 1 to 3 until tutorial this week, today, and then today and tomorrow. Lab demos 1 to 3, including this Thursday, and PS1, PS2. These are the materials for quiz 1. The first part of this course. I test this to CATFA. He scored 89 out of 100 in 80 minutes, just minor mistakes. So if you are given 100 minutes, hopefully you are able to match the score. For those who have my CP book, if you study my page 42 to 47, you do all the programming exercises listed there. There are about 28 problems related to BST, heaps, about 28. If you do one of them in about 1 or 2 hours, in 28 hours or maybe 50 hours, you will know, you will be able to answer all my questions in quiz 1. Because the question in quiz 1 will be a modification of those existing problem sets. So if you are diligent enough, you can try all problems listed in this page, and definitely you'll be able to answer my question in the final in quiz 1. Right. Okay. These are the format, same as last year. The only change is this: in section 3 is no longer about PS1 and PS2 extension, but some other BST and heap questions independent of PS1 and PS2. Total 100. The differentiator questions is the last one. So try not to touch the last one until you have completed the first 4. Okay. And each of them usually have short answers. If you try to write longer than necessary, you are just wasting your time. I am looking for the main ideas, not the full details. Okay. And I think 85 marks is doable. As that's why I'm expecting average 70 out of 139 students in this class. Right. Then I have an update for tutorial 3 this week. As some of you may have known this, but I haven't made proper announcement yet. Cat's father passed away last Friday, so he is now back in Malaysia. Therefore, he is unable to conduct his 6 sessions this week. So, Cat's session 07, 8, 9 of today will be replaced by Prof. Leong Hon Wai, Nguyen Trung Hiu, Lab TA, and Pang Yan Han, tutorial TA. And for tomorrow, tutorial 2, 3, 4 will be replaced by Prof. Leong Hon Wai again and myself. Prof. Leong Hon Wai is the teacher who teach me heap data structure 12 years ago, so he is my master. You will get the better TA. But hopefully Catfa can recover soon and come back with us next week. Right. So this is for this week. So for tutorial 7, 8, and 9, if you see different tutor today, don't be alarmed. It's because of this change. Right, now about 80 or 90 students. Can you take out your clickers and tell me what is your status as of today? Is this clicker system working? No? No, okay. Wait for a while, I'll have to restart this. Yeah, can. Okay, can you try pressing your buttons again? Yeah, PS2 has been around for 5 days now. It's about priority queue. Where are you now? Yeah, 30 clickers. Good. We have solved to have not read this. Try to do that earlier because there is a reason why I upload such problem set 1 week earlier. It's for you to read it first. And the more exposure that you have, the better you are in answering the problem set. If you leave it late, you will play catch up. Today we are going to discuss chapters 1 in tutorials, and then I believe even up to the last one you should be able to up to chapters 2 should be doable by this Thursday, and the last one requires modification of binary heap or something else. Right, so I want to know your behavior. Is it the same as last year's or is it different now? So what will you do? I recommend 6 hours for problem set. Are you going to stop at 6 hours? Or are you going to keep improving? Or depend on my workload? Or the 4th option, I'll wait for my friends to finish it first. I will not know who clicks what. So if you say number 4, fine. Yeah, let's see. 51. Depends on my workload, but mostly option 2. Okay. Alright. I know that this game system allows you to cooperate. The objective is to beat the system, which is my problem set. So you can cooperate, but you cannot cooperate up to coding level. algorithmic level, fine. Sharing test cases, fine. Right. You can even ask students outside this class. You can ask your seniors. You can ask other lecturer if you want, if you dare. The idea is once you get the solution, code it yourself, so that you get you internalize the concept. So there is one teacher of mine 12 years ago who said this to me after tutorial sessions. So it's a philosophical statement. Listen to this carefully. So after tutorial sessions, he said something like this. So I have explained to you the answers of today's tutorial. Most of you agree that the answer is correct. But you cannot say that those answers, those knowledge is currently yours. It's still mine, the TA, still the TA. Because only after you redo the questions with different examples, different numbers, and get the same correct answer, then you can say that the knowledge is yours. If you only listen to others and don't try it yourself, the knowledge is still your friend's, me, still mine, not yours. So to internalize it, you have to do it yourself. Time. How much time you spend for PS1 plus PS2 divided by 2, the average time of these two PSs so far? I have done the same task in Facebook, and 24 of you have said something. How about the rest? Okay. Right. So this shows us that there are people with that spend more than 6 hours, which is this is a good thing and a bad thing of this game system. The bad thing is it becomes uncontrolled time spent for you, for students. Right. The good thing is by having this done at home, I'm able to bring a learning experience not just inside the classroom but outside. And the next slide will tell me whether this is preferable or not. So what do you want? This number 1 or number 2? I have the answer from last year, so whether this is still same or not. Yeah, same. Last year, majority also prefer this kind of system over the stressful sit-in lab. By having take-home assignment like this, you can code at your own pace, get the point that you deserve. No more crying because of minor bugs and lose almost all the marks, because you can test all your code by yourself. Test your code with various test data posted in forum. Right. All right. So we will move on to the main topic of today, which is the second part of 2010. I remind you that 2010 has 3 parts. The first part is nonlinear data structures. We have done that already. We have discussed binary search tree, the balanced version of binary search tree, and priority queue, binary heap data structure. So we have done that. Now we have moved on to the second part, which is graph data structures and algorithms. We will start with 2 data structures for graph, adjacency matrix and list, and then 2 graph traversal algorithms, depth first and breadth first algorithm. This lecture note is a bit long, and I don't want to rush. Therefore, at some point this will be cut. The second part will be stopped before I complete this lecture note, and I will continue that next week. And next week's material happens to be quite short, minimum spanning tree, so we should be able to cover 5 and 6 by end of next week. Right. And I know that majority of you have taken cs2010 or discrete mathematics, although not everyone. Minority haven't taken it, but 99% have took this module 1231. So the next few slides will be a revision, be something that you have seen earlier. So I will not go in depth. To prove that you really have known things from 1231, can you give me a nomination? What are the terms that you already know, mostly from CS1231, discrete mathematics? What are the terms that you already know before this lecture? Okay, my knowledge of last year's behavior is this. Number 2, number 4, and number 9 will be low. 5, 6 will be quite high. 1, 3 will be quite high because of 1, 2, 3, 1. So 1, 3 is high. 4 is low, right? Yeah, right. And then 5, 6 will be medium, which is because of 1, 2, 3, 1. Number 9 should be low. Oh yeah, Bellman Ford should be low because most of you prefer Dijkstra rather than Bellman Ford. Yeah. Right. So these are the numbers, rough numbers. But then CS1231 has a difference compared to 2010. 1231 mentions this same terminologies as algorithms only. They discuss in 1231 you discuss Prim's or Kruskal algorithm, you discuss form of depth versus breadth versus something like that, but in terms of algorithmic level. So have you coded that? Have you implement those that you said you already know? Have you ever coded minimum spanning tree algorithm? Have you ever coded Kruskal's algorithm? Have you ever coded a Dijkstra algorithm? Have you even coded depth versus algorithm? Tell me. Why there are only 4 now? Hey, so there's a difference between knowing and internalizing, right? So there are these are the difference that I want to highlight between 1231 and this module. Even if you say, I've seen this before, I know my minimum spanning tree, I know depth versus breadth versus. Have you ever coded? Why only 7 clickers? 7 foot. No one else? Yoo-hoo. Okay, I'm not going to wait. So far, 7 of you has done this. Only 5 have done depth versus breadth versus. This is a far cry compared to this, right? You say you know, but haven't tried. Knowing in algorithmic level does not always translate into implementation level. And if you work in software engineering company later on, your boss will not say, hey, can you please code a minimum spanning tree algorithm for this? Oh, I understand, but I cannot code it. Find someone else. Then he will really do that. He will fire you and find someone else who can code it. Right? So implementation is important, and you will do that in PS 345. 345 will be about graph. PS 3, 4, and 5 will be about graph, data structures, and algorithms. You will be a kind of forced to implement all this. You will be forced to implement all this. Not all this, some of this. Okay, so a quick revision on graph terminologies. So graph is an extension of what you already know in previous lectures. We have seen binary tree earlier. This is a picture of binary tree. We have nodes, circles like this. We have edges. We have direction of the edge. Sometimes we have weight associated with the edge. But in general graph, there is no notion of root. There is no node that we can say is a root node. We don't have parent-child relationship or ancestor-descendant relationship. We don't have it in general graph. Okay, so this is an example of general graph with at the moment 1 to 6 vertices. I label the vertices 0, 1 until p minus 1 until 5. There are 6 vertices here. Right. For CS2010, most of our graph will be simple graph. Simple graph will be a graph where we don't have more than one connection between pair of vertices, and we don't have self loops where there is an edge between a vertex to itself. We don't have that. Simple. Right? A simple graph has has 3 vertices, and there can be 0, 1, 2, 3 until n choose 2 possible pairs of edges, possible edges that connects pair of vertices. So for example, this is a graph with phi equal to 6, e edges equals to 0. There is no edge, right? Okay, 5 is a vertex. Okay, so suppose I add one edge, 0, 3. At the moment there are 6 edges, 6 vertices and 1 edge. Okay. If the edge has no arrows, this edge is bidirectional. Means that 0 can go to 3, 3 can go to 0. And 0 and 3 are called neighbor, or they are called adjacent. If I have an arrow in the one of the end or both end of certain edge, that edge is called directed, has direction. So 3 arrow 4 means that 3 can go to 4, but 4 cannot go back to 3. And then if there is a number associated with an edge, this is a weighted edge. But if because there is no arrow here, means that it's bidirectional, or there is no direction, undirected. Right. So we can have more and more edges until n choose 2, until full complete graph. Okay. So graph is almost everywhere. So today most of us are in. Okay, I force you to join Facebook, whether you're willing to do that or not, for the sake of our game system. So all of us are inside this social network, Facebook. But Facebook is not the only social network. There are others like Twitter, LinkedIn for professionals, and Friendster in the past. So I started social networking with Friendster. But when I prepared this slide, I visited Friendster, and now it has been changed into a gaming site. It's a different now. It's no longer the social network that I know in the past. By the way, I found my wife from Friendster. Really? Okay, so maybe you can find your soulmate from Facebook. Maybe. Alright, continue. So, more terminologies that you probably have seen or have heard before on simple graph. Sparse and dense. It is related to how many edges that you have in your graph. Sparse means you don't have that many edges. Dense means you have many edges, but there is no guideline on how many edges that you need to have before you can consider dense, or how small, so it's not a fixed number, so it's an ambiguous number. But you know that, for example, the graph on top is more sparse than the graph below, right? The graph below has so many edges, but the graph on top has much lesser edges. So it's just a relative comparison. In fact, the graph in the bottom is called complete graph. Complete graph is a simple graph with n vertices and all n choose 2 edges. So every vertex is connected to every other vertex. Every vertex is connected to every other vertex, and so on. By doing so, you have a complete graph. Okay. Next terminology is inside, in-out degree, in or out degree of a vertex. So number of incoming or outgoing edges from a vertex. So for example, this is sparse graph, this is dense graph. A dense graph with cs7 choose 2 or 21 edges, you can count. You can count that this is really 21. Okay, for undirected graph, the number of incoming and outgoing edges of a vertex is the same. So for vertex 5, I have 5, 2, 5, 4, 5, 3. 3 outgoing edges. And I have 3, 5, 2, 5, 4, 5. 3 incoming edges also. So in and out degree of vertex 5 are both 3. For undirected graph, there's no such difference. But later, when I show directed graph, there can be some difference. Next, path. Path is a sequence of vertices adjacent to each other, and there is usually when we are discussing paths, we are referring to simple paths when we don't repeat vertex. We don't repeat. So, and then a path length or cost depends on what kind of graph that we are dealing with. For undirected graph, the cost of a path is number of edges that we use. For weighted, it's the sum of edge weight that you use. And then for cycle, path that starts, go to another vertex, and come back to the same vertex. And we have no repeated vertex except start and end for simple cycles. So this is an illustration for such thing. So all of us are familiar with this picture. Singapore has a good network, transportation network, although it's crowded nowadays. Okay. All right. So path. There is a simple path from Clementi to Outram Park, MRT. They are with length 7 in terms of number of ages. See, Clementi to Dover, Dover to Buona Vista, Commonwealth, Queenstown, Red Hill, Tiong Bahru, Outram Park. There are 7 stacks. So if I want to go from Clementi to Outram Park, I will not do this, right? Clementi to Buona Vista, stop, and then from Buona Vista go back to Dover and then stop. From Dover continue to Outram Park. I'm not going to do that, right? That is waste of time. So usually for going from one place to another, we don't usually cycle. We don't repeat vertex. Okay? We just go from starting point to ending point without repeating vertices. And for some of us who live in the north, you may use this LRT quite often. For people around Sengkang area, LRT, right? So this LRT forms a loop. It's a cycle. It starts from Sengkang MRT, circling around certain neighborhoods over there, and come back again in Sengkang MRT. What happens if you go and you cannot come back? It's a bit funny, right? Usually there is a loop that comes back to starting position. Alright, so graphs can be used not only to model transportation network, but for many other things in real life. Some of you are Googling here and there now, or Facebooking maybe at the moment. So you're using internet connections, right? Internet connection can be modeled as computer network, can be modeled as a graph, where your computer is a vertex, other computers is another vertex. If you can contact that other person, you are connected with an edge. Or you can contact other PCs via a series of routers, satellites, and so on, and your message delivered to the other person. Communication network, computer network. And same thing with communication network, where whenever you use this thing, handphone, whenever you make a call, you establish connections. That connection can be viewed as an edge connecting you with maybe a satellite, and that satellite sends your message to another receiver, another handphone, or something else. Establish a communication network there, or communication graph over there. Then graph can also be used not just for things that you can easily see, but something that maybe some of us, if no one else told you about this, you may not think there is a graph here. So this is a map of United States of America. We can change it to another map, and this is a 2D map. 2D map of the world. I want to color this map so that between adjacent states, right? Adjacent states, I don't have same colors. So let's say, right, my geography is not that good. Okay, this is my Florida, and this should be South Carolina. So this is yellow, and this is green, right? So what happens if this is green and this is also green? You cannot differentiate. Right. So usually for map between adjacent states or adjacent countries, we will color them with different colors. So so the question is, how many colors do I need to color this map? How many colors? Who said it? 4. Yeah, so that's correct. It's 4-color theorem. It's true because of this map is a planar, it's a flat, a 2D map. So how to solve it? So we know that it's maximum 4, right? But how, if I give you this picture, how can you color this? Any suggestions? Do you know how to do it? You create a graph out of this. What is the vertex? Neighbors, okay, and then Okay, so rough idea is like that. Yes, for states will be a vertex. If you have neighbors, connect those vertex with an edge. Means that if I want to color, so this one is connected to this and this, right? So if I color this as red, I can no longer color any of my neighbors as red. So suppose I take red and this is green, then I can no longer color green on my neighbors, direct neighbors. So I try, this is semi brute force, and optimize backtracking to solve this. The easy way is to do that. You model this state as vertex. If you have conflicting neighbors, you draw an edge between them, saying that if I choose a certain color for this state, I cannot choose the same color for my direct neighbors, and so on. Okay. And you can only stop when all states have been given a color that doesn't conflict with any other state. Again, but this is level 5. This is combinatorial and graph algorithm. So you may not see this in 2010. Just for you to know. Okay, yet more terminologies about graph. Component, connected, reachable, subgraph, things like that. Okay, component is a group of vertices that can visit each other. For this module, I will drop the notion of strongly connected components. We will leave it for higher level course, because that is a slightly more difficult problem. So for whenever I mention component in 2010, it will be just for undirected graph. So component is like this: 0 connected to 1, 1 connected to 2 and 3, and also 0, right? So 0, 1, 2, 3, and 4 can visit each other. Right? If they can visit each other, they belong to the same component. But look at 3 and 7. There is no way I can move from 3 to 7 following some kind of edges. That's why I said 3 and 7 belong to different components. 5 has no edge, so 5 cannot go anywhere. So it is a single component with a single vertex, and it is isolated. It's also isolated. So if you are like this, it's okay. Game system is supposed to have you connected with each other, beating the game, right? Beating the system. So if you don't work together, you only try to solve the PSS by yourself. You can if you are really, really good. But if you want to take advantage of that system, try to talk to each other, share test cases with each other, challenge each other, discuss algorithmic ideas, so that you are not like this vertex number 5, isolated, without help from anyone else. Okay. Right. So connected graph. So a connected graph is a graph with only one component. This graph is not connected because I have 3 components. Okay. I have 3 different groups of vertices that can visit each other. A subgraph. Subgraph is simply a subset of vertices and their corresponding edges of the original graph. So if this is the whole graph, I can take 7, 6, 8 for example, take them out. So I have formed a new subgraph, 7, 6, 8. Of 3 vertices, 2 edges. Like that. I can do that. Alright. Some more terminologies, the last few slides. Directed acyclic graph, or what we call as DAG. Directed graph is a graph with arrows where all the edges have direction. So like 0 go to 1, 1 go to 2, and so on. 0 go to 1, if the arrow only go from 0 to 1, it means that I cannot go back from 1 to 0. Acyclic means that this graph, by definition, has no cycle. So can you verify on the right side here? Do you find any possible cycle? So 0 go to 1, 1 go to 2, but can 2 go back to 0? No. 2 go to 3, 3 go to 4. Can 4 go back somewhere behind, back to 0 maybe? No. Back to 1? Also no. So you try. By following any sequence of edges, you will never find any cycle. So if that's true, your graph is classified as directed acyclic graph. We will see DAG, DAG, or DAG. We usually call it as DAG. Quite often when we discuss the third part of cs2010, dynamic programming. Because dynamic programming, before I discuss the true form of dynamic programming, I will just link them with what you will learn in the next 4 lectures with graph. Dynamic programming can be viewed as operations on graph, algorithms on graph, algorithms on DAG to be precise. This is a special type of graph that we will see quite often in 2010, especially the third part. Now, with a directed graph, I want to highlight out and in degree. Okay, out degree of vertex 0 is 2. Why? Because there is 0, 1 and 0, 2. So 0 has 2 outgoing edges. And in degree of vertex 2, for this case, happens to be also 2, because there are 0, 2 and 1, 2. There are 2 edges coming to vertex 2. Now let's take another vertex, vertex 3. Vertex 3 only has 1 outgoing edge, 3, 4. So out degree of vertex 3 is 1. But 3 has 1, 3 and 2, 3. 2 edges coming inside 3. So in degree of 3 is 2. So with directed edge, the notion of in and out degree of a certain vertex, there can be different numbers. Alright, 3. So after directed acyclic graph, we also have notion of 3. We have seen 3, but what we saw in the first few lectures is binary 3, where the 3 has exactly at most 2 children. Now I can choose to relax that condition of binary 3. I can for general 3, I can have more than 2 children. I have more than 2 children. Right. Now this is a 3. Right? 8 has 5, 1. 1 has 3. 3 has 7, 2. A more general definition of a 3 is I am a connected graph. I have E equals to phi minus 1 vertex, and there is only one unique path between any pair of vertices. That is the more general form, general definition of a 3. Let's check this this picture. Is this connected? Yes. 5 can visit anything else. 1, 2, 3, 4, 5, 6. There are 6 vertices, and there are 5. 1, 2, 3, 4, 5. There are 5 edges. Phi minus 1. And then this is something that not everyone aware. There are only one unique path between any pair of vertices. Let's take 5 and 2. You can only go 5, 8, 1, 3, 2, right? There is no other way to traverse the tree between 5 and 2. You take any other random vertex, 7 and 2. There is only 7, 3, 2. There is no other way. Because, for example, if you take 7, 3, 1, 3, 2, then it's no longer simple path. Right? For 3, there's a unique property of that. And then finally, bipartite graph, a graph where you can partition into 2 sets. One on the left side, one on the right side. The edges only crossing between the 2 sets. There are no edges between members in the same set. So a real-life application of this is you can view the blue vertices as male, and the green vertices as female, and a marriage is only between male and female. Okay, that's bipartite graph. Okay, so we have reviewed some terminologies. We will move on to the 2 data structures. So I can discuss the 2 data structures in 2 minutes, 1 minute each. I can. Right? But I'm going to spend 5 minutes each to discuss the 2. Right? So because adjacency matrix, I can say it's just a 2D matrix, 2D array. Adjacency arrays is just an array of neighbors. I can say that, but we will go into deep a bit. We will explain more details about these 2 data structures and some basic application of what we can do with these data structures. So you have seen a graph. I want to know graph has vertex, has edges, have paths, and have cycles, can have components. If I just store the information about the vertex only, the vertices only, will I be able to reconstruct my original graph again? Suppose I have a Facebook graph. If I just remember that Facebook has 1 million users, for example, I just remember that information. I know that user A has this profile, user B has this profile, and up to 1 million users. If I just store that information, will that be enough? Yep, it won't be enough. It will not be enough. Why? Facebook. Imagine that if Facebook only remembers profile or your profile, but it doesn't remember who are your friends. So Facebook without friends, funny, right? You only have your profile. Nobody sees your profile except yourself, and no one knows your profile except yourself. What's the point of having the account, right? You have a social network for others to see, to share your life with others. So you need connection, the ages information also. Okay? So that's why we need data structures to just that store not only the vertex information but also age information. The first data structure is adjacency matrix. It's very easy to explain. It's a 2D, two-dimensional array. If the graph is unweighted, it's simply a two-dimensional Boolean array containing zeros or ones. So adjacency matrix Ij, row I, column j, contains value I if there is an edge between I to j, directed edge I to j. Otherwise, adjacency matrix Ij is simply blank or zero. Okay, for weighted graph, we can change the notion of Boolean matrix into integer matrix, where we store the weight of Hij if there is an edge between I to j, and zero otherwise. Because zero is usually identify that there is no edge. So let's take a look at this picture. I have 1, 2, 3, and so on. Let's see, 1 is connected to 2 and 3. So row 1 is connected to row 2 and row 3. Let's take another vertex 5. 5 is connected to 3, 4, and 6. So row 5 is connected to column 3, column 4, and column 6. Okay, this picture is one-base indexing. In implementation wise, you may want to use zero-based indexing. So the vertices is numbered from 0 to p minus 1. So here's from 0 to 6 instead of from 1 to 7. It's just an implementation choice. Now I want to highlight the notion of space complexity. So all this time we are talking about time complexity. What's the time needed to perform a certain operation? But today I want to highlight that time is not the only thing that matters in implementing algorithms. There is also a notion of space complexity. So if we have a graph of p vertices, do you realize that to build a 2D array of p times p, we need p square cells? P square cells, there are p square cells. Okay, p is a shortcut of the notion of cardinality of set, or the number of items in the set. P is a set of vertices. Bar, p bar means number of vertices in the set, but I will just abbreviate it as p. Right. So if I want to store a graph with p vertices, I will need p square cells. So if I have a graph with 100,000 vertices, can I use adjacency matrix? Okay, let's see. Alright. 25 of you are correct, but 10 are wrong. Just now I said 3 equals to if I have a graph with 3 vertices, I will need p square cells to store this graph. So if 100,000 square, very big. And you can argue that today's computer memory is big, but if you store it that way, is your computer only running, only storing your graph only? No, right? No. Your computer will store more than just your graph. If you store this PowerPoint slide, running operating system and so on, it will be much more than that. And if you say, okay, 100,000 probably can, what if I give you 1 million? Even impossible, more impossible. 1 million square will be 1 million is power 6, right? 10 power 6. Square will be 10 power 12. Is 1 million gigabyte. Yeah, 1 million gigabyte. Do you have a memory of that size? 1 terabyte. Yeah, it's a 1 terabyte. It's hard. Too big. So Facebook, it has millions of users already. Definitely, it doesn't use adjacency matrix. It uses something else. Okay, let's see another alternative data structure called adjacency list. The format will be array of lists, array of P lists. One for each vertex in P. For each vertex, I have a list. For each vertex, I have a list. And this list is a list of vertex i's neighbors. Right. So, for example, 4 has 5 and 2. So, in row 4, I have 2 and 5. 5 has 4, 3, and 6. So, in row 4, I have in row 5, I have 3, 4, and 6, and so on. And usually, my neighbors are ordered in sorted order. In terms of programming complexity, in terms of practicality, it's easier to do it this way, where you list down your neighbors in ascending order based on vertex numbers. What if your graph is weighted? We will use pairs of information. I know who are my neighbor and also the weight of this age. Because if I only store my neighbor ID, I don't store the weight, I lose this information. So I have to store a pair of information. Who are my neighbors? And between me and my neighbor, what is the age of, what is the weight of my age, of this age? Okay. Now the space complexity is no longer P squared, but P plus E. What is this? E is the shortcut of cardinality of set E. Shortcut of number of edges. Okay. The number of edges in the graph can be in a simple graph can be as large as P squared, but most of the time it is much less than that. Okay. Let's take a look. Why this is P plus E? First, it is at least P rows, right? So there's the term P here. But then for every row, you can have up to can have P minus 1, can have only 1, can have 0, and so on. Right? But if you sum all this, it becomes 2E. Why 2E? Because, for example, vertex 5 will store 3, 4, 6, right? Vertex 5 will store 3, 4, 6. So vertex 5 will store 3 outgoing edges out of 5. But then 4 will also have 5 inside. See? 4 will have 5 inside. 6 will also have 5 inside. 3 will also have 5 inside. So every edge is counted twice because of bidirection. Right? So the total number of edges here will be 2E. 2 times the number of undirected edges. But 2E, you can drop the 2, right? So it's just E. So P plus E is a common notation in graph to say that the space complexity or the later time complexity that involve P and E is the maximum of these two. Okay. In the past, in 1020, you learned that if you have n plus n squared in asymptotic notation, the lesser value, the lesser power will be dropped, right? N plus n squared, n will be dropped. But here, phi and e are two different numbers, two different variables. So you can't drop any one of those without affecting the meaning. Why? For a sparse graph, phi can be greater than e. So imagine I have phi equals to 1 million vertices, 1 million Facebook users without friends. So e equals to 0. Can, right? So phi equals to 1 million plus 0. So the e part is the one that should be discarded because it doesn't have 1 million versus 0. 1 million is much bigger. But in actual reality, in Facebook graph, something like that, you have 1 million vertex, you can have up to 1 million square edges. which is, but it's not possible unless everyone in the world knows everyone else in the world, right? So it's not possible. So usually one of us have 100 friends, 1,000 friends. Some of them are true friends, some of them are just friends, some of them are, they just add you randomly, right? But the total number of edges there will be much less than phi square, but it will be greater than phi. If, for example, Facebook, let's connect with Facebook graph. If I have phi users using Facebook, and each user know more than one friend, let's say every user knows 2 friends, then the number of edges actually 2 phi, right? 2 phi. If every user knows 100 other users, the edges will be about 100 phi, right? So phi plus 100 phi, who should be discarded? The smaller phi, right? So here we see that depending on the on the structure of the graph, phi can be larger than e, or e can be larger than phi. Most of the time, e is larger than phi, but it's not always. Therefore, the notation used will be phi plus e. It can be either one. We don't drop any of the term until we know for sure that one of them will dominate. For example, if I know that the graph is a tree, I recall few slides, previous few slides, in a tree, e equals to phi minus 1. Right? So this is phi plus phi minus 1. Right? So 2 phi minus 1 or phi. So in a tree, phi plus e is actually phi, because the e equals to phi. But now let's look at complete graph. Complete graph have phi vertices and phi square edges. So this becomes phi plus phi square. You drop the phi. In complete graph, space complexity is phi square. Something like that. That's the way we use it. So, a follow-up question. What can you do if you... if I have a graph, the same graph with 100,000 vertices, can I use adjacency list? And there is an option depend. Every time I have none of the above or depend, something like that, it can be harder. Let's see. Why? Okay. Who says depends? Okay, you're wrong. Why? Correct. Yes. Just now I stopped saying that phi equals to 100,000. But then the space complexity of adjacency list is phi plus e, right? And just before I flash this slide, I say that if e equals to phi minus 1, if the graph is a tree, phi plus phi minus 1 is just phi. But if the graph is a complete graph, phi plus phi squared is the same problem as previous slide. Right? So Shiran is correct. Depends on what happened with your e, because here I only mentioned that phi is 100,000. If phi is 100,000, can I use adjacency list? Depends on what kind of graph that you have. If your graph is very, very big, a number of edges very big, then even adjacency list may not be possible. So, how do we code this? Simple. For adjacency matrix, you just need to use 2D array. You can create a 2D array of size phi times phi. For adjacency list, it's slightly more difficult. There are several ways of doing this, but for me, I will use a factor of integer pair. Right, so why is this? What is this? Yeah. Let's discuss integer pair first. Integer pair is a simple Java class that contains 2 integer values. I call it first and second. It is constructed by creating this simple constructor that simply copy the value of first and second. And there is a nice compare to method that will compare this pair based on the first value. If the first value is already different, I will use them to compare. But if the first one is the same, I will use the second one to compare. We will use this later for sorting this pair. But for now, you can ignore this for now. And then I have a assessor function that can report what's the value of first and second. So once it is constructed, you cannot touch it anymore. can only assess what's the value. Okay, now we are going to use adjacency list for most of our problems. So adjacency list will be most of our graph problem in 2010. Factor of integer pair. So why do we use integer pair? Okay, first we need to store pair of information for each age. What is the neighbor ID and what is the age weight? Because there are two information, we cannot just use one number. We group the two numbers together as a pair, and we store this integer pair. Okay, what is my weight? Is a double. Okay, change the class name from integer pair into pair of integer double, whatever, so that you can store the weight as a double, as a floating point number. Now, why do I use factor of integer pair? See the green one, factor of integer pair. For the auto resize feature, because if you have k neighbors, from an empty factor you add k times, your factor becomes of size k. I don't need to set a certain specific size for my list of neighbors. If I fix the size, if I exceed the size, my program will crash. I will just use a auto resize feature of Java factor to help me with that. You can change this to a list or array list if you want to, so you don't have to use the class factor. Finally, why do I use factor of integer pair? The blue one. It's for factor indexing feature. For the last one, you need to use factor or array list. You cannot use linked list. Okay, because I want to know, for example, I want to access neighbors of vertex 5. I need to be able to immediately go to row 5 minus 1, row 4. If I cannot do that instantly in O1, the performance of many graph algorithm will be penalized. So for indexing feature, I need the last part to be an array-based solution. And again, I use factors so that I have flexibility with size. Right? So we have this question and then we stop for now. So you have been exposed with adjacency matrix and adjacency list. Which one should be our default choice? Okay. Okay. If you notice my style, you should have noticed that most of the time the answers will be depends. If you have noticed PS1 and PS2, most of the time the answers will. Some of you may propose this idea, the other may propose another idea, and I can say both are correct in their own interpretation. Most of the time I will say that, because for adjacency matrix and list. Okay, you say adjacency list is more efficient most of the time. Okay, yes, maybe. But if I am dealing with a small graph, do I need that flexibility? So suppose I'm working with p equals to 100, small graph. I may be better to use matrix, because in adjacency matrix I can know whether I and j are connected or not by looking at row I column j, row I minus 1 column j minus 1, instantly, O1. Whereas in adjacency list, I need to explore my list, whether I have this neighbor or not. So for certain cases, matrix can be better, right? But not always. So the answer will be different. We take a break until 11:08 using that clock, 11:08, and then we'll continue. We'll try to cover as many slides as possible from today's second note. And for those who come late, I flashed this at the beginning. For those who came late. What is your time slot? 9. That is in morning. Oh, yeah. And up to 2 is 2:45 no longer. And not in but you can use your question to do this one for and then this is okay, let's continue. So we have seen adjacency matrix and adjacency list. Now what can you do with just these data structures? Apparently not much, but we can already do something. Here are some trivial things that you can already do. You can count how many P's, how many vertices are there in your graph. It's simply the number of rows in list and matrix. In a matrix and the list, if you see 7 rows, then yeah, it will be 7. Very trivial. And most of the time, this number is stored elsewhere, so then we don't have to check. Enumerating neighbors. This is a common operations in graph algorithms. So for every vertex in adjacency matrix, for example, vertex 2, I go through every vertex and see how many 1 I have. So 2 connected to 1, connected to 3, connected to 4. See, 2 is connected to vertex 1, vertex 3, and vertex 4. Right. Let's take another vertex 6. 6 is connected to 5 and 7. Am I right? Yeah, 6 is connected to 5 and 7. So in adjacency matrix, I have no choice but for every row, for a certain row that I want to investigate, I have to check every column, find all those 1s, find those that are non-zeros, means that find those with edges. Therefore, the time complexity to enumerate a neighbor of a certain vertex is OV for adjacency matrix. Thus, I have to scan the entire Pj for all j 0 to c minus 1. But for list, adjacency list, I can just scan adjacency list at index P or index P minus 1 if you prefer a 1-base index. So suppose I want to find at row 5. Okay, I just jump to this row 5 and move 3 times, 3, 4, 6, and I will know that 5 is connected to 3, 4, and 6. But in order to do this, your adjacency list must be a factor of integer pairs. The outside must be a factor or array, so that you can immediately jump to that particular row. Otherwise, you cannot do this. So what's the time complexity? It's no longer V. I use another variable called, usually people call it K. You can use another variable name, but for graph terminology, usually it's K, where K is the number of neighbors of a vertex P. So if there are 3 neighbors, K will be 3. If there are 5 neighbors, K will be 5. And this is adaptive, right? Depending on how many neighbors do you have. Of course, K can be as large as P minus 1. P, yeah. But K can also be as low as 0. And this flexibility is important. And this too is the main difference of certain graph algorithm performance later on. So remember this difference. Adjacency matrix use OV to enumerate the neighbors of a certain vertex. Adjacency list only OK for doing the same thing. Okay, counting E, the number of edges. Again, for matrix and list, we slightly need different behavior. For adjacency matrix, you need to traverse the entire cells, p-square cells, count how many ones are there in your table. Right? It becomes p-square. Right? For adjacency list, you go through all p lists, and for each of them, you sum how many edges you have in that list. So p plus e, sum of length of all p lists. Again, sometimes this number is stored in another variable so that we don't have to recompute this every time. This is the one that I say matrix will be better. And just checking the existence of certain H. It will be O1 for adjacency matrix. So for example, I want to know whether H56 exists or not. So I just go to row 5, column 6. There is a 1 there. So yes, it exists, 5, 6. How about 5, 7? There is no H, right? So if I go to row 5, column 7, I see a blank. Blank means here is 0. I don't draw the 0. So there is no 5, 7. How about adjacency list? I have to, for example, I want to check 5, 6. I have to go to row 5 and check all my neighbors. Do I have 6? No, no. Yes, I have 6. So yes, I have 5, 6. How about 5, 7? I go to 5 again. Do I have 7? No, no, no. Until the end of this list, I cannot find 7. So to check the existence of an H, it is OK not OK, that's O bracket K for adjacency list. You have to traverse the entire neighbors to check whether you have it or not. Okay, there are a few others. I will leave them for our PSS. If I enumerate everything, I don't have test questions. Okay, so with this matrix and list, we can play around with that a bit and do something with them. Trade-off table. What are the pros and cons of adjacency matrix and list after our discussion in the past 1 hour? So the pro side of matrix, you can check whether Hij exists or not exists instantly in O1. And it's good for dense graph, because for dense graph, it's good for small dense graph. They must have a word small there. Why small dense graph? Because if it's big dense graph, you can't even use matrix in the first place. But for small dense graph, then you will see lots of ones, and less zeros, less zeros. So whether you use matrix or list will not have any effect, and having matrix will speed up the checks of existence of edges. And then later on lecture 11, there will be an algorithm for Floyd-Warshall that prefers matrix over list. For list, the pro is we need O bracket K to enumerate neighbors of a vertex. It's good for large sparse graph, and it is good for most graph algorithms that will be discussed in 2010. It uses only V plus E space. The bad side of matrix is OV to enumerate neighbors. It requires V square no matter what type your graph is. The bad side of adjacency list is OK to check an existence of an edge, and a little bit of overhead in maintaining the list, because if you realize that we are using factor of factor. Factor is not a lightweight data structure. It contains constructor, built-in private data structures, something like that. It is not cheap. It has some additional overhead compared to just 2D array. Right? 2D array, nothing else. It's just a 2D array. Okay, so no more break. Okay, we already did the break. So at home you can play around with this. Okay, so we have not me, a student, third year student called Ji-Chun have helped me build this thing. So if you want to know if I only have a vertex 0, what's the adjacency matrix? It's simply 0. Right? You have two vertex 0 and 1. What's the adjacency matrix? 2 times 2, all zeros, right? I have two lists, all blank. If I connect 0 and 1, then 0, 1 will be 1, 1, 0 will be 1. 0 will have 1 as the neighbor, 1 will have 0 as neighbor. If I connect 1 with 2, for example, like this, then 1 will be connected to 0 and 2, right? 2 will be connected to 1 only, and so on. So you can play around with this, and every time you add edges or you delete edges, the representation will be shown instantly. I hope that by using this visualization, no one here in this room can say that I don't understand this anymore, because you can try all your examples by yourself and draw your own graph and verify your understanding whether it's the same or not. Next week we are going to see what's each list, but next week. So for now you can already know what's this list. Right, so with just adjacency matrix and list, we can store the graph. But storing the graph is just one thing. What we need to do is we want to explore the graph, analyze the graph, do something with it. We need a way to check or traverse or to explore our graph. There are two classic algorithms on exploring graph. One that we call as depth first, and the other that we call as breadth first. And in my book, it will be chapter 4, the early part of chapter 4. Right? So hopefully I can reach up to depth and breadth first explanation. And if we don't have time, the application will be deferred until next week. It won't affect your PS3, because PS3 will only due during the test week. Right. So before I start with graph traversal, I'll have to link this back to what you already know. You already know that if you have a binary tree, you can traverse this binary tree easily, because you know that every node has at most 2 children. And for a binary tree or a tree, we have a notion of root. You know where you start, the root. Okay. So in lecture 2 or 3 lectures ago, I have discussed in-order traversal. In-order traversal is in the middle here. In-order vertex U, I go to my left, I visit vertex U, I process or I print it, and then I recursively go to my right subtree. That is in-order traversal. Last week tutorial, I discussed pre-order. And then for some TAs, they may also discuss the post order, the reverse of it. Okay, so pre and post is just different here. For pre, I visit first before recursively go to left and right. For post, I go right and left first before I visit the vertex. There is one more called level order, which is no different than BFS that we will see next. So, given this kind of graph, let's try the in-order traversal first. Start from root, go left, return, visit 1, go right, return, visit 0, go right, go left, 3, 2, 4. Like that. So I will have 1, 0, 3, 2, 4. For pre-order, I will visit first. Visit 0, go left. Visit 1, go left. Nothing. That's correct. Visit 2, visit 3, nothing. Visit 4. So 0, 1, 2, 3, 4. Post order. Go left, go right, visit. So 1. And then I defer the visitation of 0. Go right first, go left and right. Visit 3, visit 4, visit 2, visit 0. So I visit the leaves first before going back up to the root. That is the post order traversal. Just a quick check. What is the post order of this thing? What is the post order of this picture? Yeah, good. Fourth one, 3, 1, 4, 2, 0. So in a tree, especially a binary tree, you have a notion of root, starting point, and your neighbors are always maximum 2. Left, right. So if you want to traverse, it's also applicable for real life. If you want to go from one place to another, first you need the origin. You need to start from somewhere. And then you need to define how you want to move. For tree traversal, it's easy. The source, the starting point, is the root. The root. For binary tree, it's the root. Although there is a note here, not every tree has root. In that case, we have to select one of the vertex as the source or as the root, as in the general graph below. But for normal tree that you have seen in the first 4 lectures, the tree is rooted. You have a notion of the starting point, the topmost item, the root. But in a general graph, we don't have the notion of root. So we start from a chosen vertex. So we call this chosen vertex as the source, the starting point, the source. And the shortcut label is the S, source S. And then the movement. In a binary tree, you have at most 2 choices. You can go left, go right, or both if you have both subtrees, or stop if you are a leaf. Right? That is your choice. If you are a leaf, you stop. You have left children, go to your left only. You have right children, go to your right only. You have both left and right, you try both. But in general graph, we can have more choices. Do you realize that? Okay. A vertex can have no neighbor, 1 neighbor, 2 neighbors, 3 neighbors, or p minus 1 other neighbors. Okay? It can be like that. So if a vertex u and v are adjacent or connected, we are now in vertex u. Then we can also go to vertex v by following h u v. In a tree, in a binary tree, there is no cycle, especially if that you feel the tree that it can only go down. There is a directed edge from root to left and right subtree, but using a directed edge. And for your left children, go to left grandchildren, right grandchildren, without any directed edge. Then there is no cycle. But in general graph, we may have either trivial or non-trivial cycle. For example, I have a bidirectional edge u and v. From vertex u, I know I'm connected to v, so I go to v. In vertex v, I know I'm connected to vertex u, so I go to u. In vertex u, I know that I'm connected to v, I go to v again. If I keep doing this, your program will never stop, right? So there must be a way to avoid revisiting. We have Prof. Leong Hon Wai at the back. Prof. Leong will conduct some tutorials today. That's Prof. Leong Hon Wai. Okay, so in general graph, we may have cycles. So to avoid this kind of situation, we need another mechanism to differentiate whether we have visited or we have not visited a certain vertex. So the solution is breadth first or depth first search. So we will start with breadth first search first. And at this point of time, I don't know the class background. I know the last year's version, but is it the same as this year? So tell me, what is your rough knowledge as of now? I know that majority is at least number 2, but how about implementation? Most likely no, right? Tell me the pattern. Right, 33, let's see. Okay, up to theoretical details level. Alright. Okay. By the time you finish 2010, most of you will be in level 5. You will be able to use breadth first search for solving shortest path on unweighted graph. By the end of this course, of course, not now. For now, I will push your knowledge to this side. So, breadth first search. We call it, we abbreviate it as BFS. The most real life analogy that I can think of is a water ripple. So you have a water, you throw a rock inside. From the source, a place where your rock falls, there will be a circle or ripples forming, right? That is the behavior of breadth first search. So the key ideas is you start from vertex S, the source. If there is another vertex V that is reachable from S, then all neighbors of V will also be reachable from S. It's a recursive definition. So you start from a vertex. If this vertex is connected to vertex V, and vertex V has other neighbors, then source can also fit that other neighbors. If that other neighbors can fit any other neighbors, then source can also visit V, neighbor of V, neighbor of V, something like that. But breadth first will visit vertices in the graph in breadth first manner. Breadth first when viewed from the source vertex. So those that are immediately reachable from source vertex will be reached first, and then those that require 2 steps away from the source will be reachable next. Those that require 3 steps from the source will be reachable after the second step, after those that require 2 steps, and so on. So that's called breadth first. Okay, how to maintain such order? We will use something that you already know last semester, Q. Initially at the beginning it only contains source vertex S. Okay, then how to deal with the problem of visited vertices? How to avoid revisiting the same vertices? We have a array, a one-dimensional array of factor. We call it visited, of the size V. Initially everything is 0, or it means that nothing has been visited, and I will set visited V to be 1 whenever V is visited. So at the very beginning, only visited of the source, visited S, is true, and the rest is false. And how to memorize the path? So when you traverse, you sometimes want to memorize the path so that later on you can reconstruct the path. How to do that? We use another one-dimensional array or factor. We call it P, or predecessor, of the same size P, where P bracket P denotes the predecessor or parent of P. Okay, at this point, these terminologies may look alien, but with some examples, hopefully it becomes clear enough. Breadth versus the pseudocode is like this. At the beginning, I will initialize every visited the visited array to be all false, and the predecessor value to be all -1 or null, nothing. And then at the beginning, I will start my queue with just S, and then visited S will be true. That's the only vertices that has been visited. Now I'm going to keep repeating this main loop. While the queue is not empty, I will take out the frontmost item from the queue, normal queue, and then for all neighbors of vertex U, and for all neighbors P of adjacent to vertex U, if my neighbor is not visited yet, I will visit my neighbor. I will say that the predecessor of my neighbor is me, and I will enqueue my neighbor. That's the English word of this references. I repeat again. I start with only the source. So see, Q equals to source, and visited of the source is true. So at the beginning, Q is not empty. It contains the source. Then I will repeat this whole thing. I will take out the what is currently in front of the Q. Right? It's vertex U. And then I will consider all the neighbors of vertex U. If any of my neighbor has not been visited, I will set them to be visited. Tell that your predecessor is me, and I will enqueue you, my neighbors, to a queue. Doing so will help me visit the neighbors in breadth first manner. This is an example will clarify all things. So I have this graph. Now it's zero-based indexing. Okay. So really I have to update my slide to always start with zero-based indexing. 0 to 12. There are 13 vertices. Suppose the starting vertex or the source is the one in red, vertex 5. So as I said at the beginning, I only have vertex 5 in my queue. So what do? I take out 5 out of my queue, and then I look at my neighbors. My 5 is connected to 1, 6, 10 in that order, increasing order. So 1, 6, 10. So I will enqueue 1, 6, 10, and I will say predecessor of 1 is me, 5. Predecessor of 6 is me, 5. Predecessor of 10 is me, 5. So the predecessor information is stored as the 3H, the red H's here. Now look at the frontmost item in the queue. It's 1, right? So I take out 1, and I look at the neighbors of 1. What's the neighbor of 1? 0 and 2. So I will say I take out 1, 6 and 10 move forward, right? And then I look at 0 and 2. 0 and 2 has not been visited. So I say 0, my predecessor is 1. 2, your predecessor is 1. And I enqueue 0 and 2 at the back of my queue. Enqueuing at the back of my normal queue. I repeat the process. I take out 6. When I take out 6, I will look at the neighbor of 6. 2, 5, and 10. 2, 5, and 11. But here, 2 has been visited, right? It's already there. 5 is the source, already visited. 11 has not. So, I will say 11, you are visited now. 11, your predecessor is me, vertex 6. And I will enqueue 11 at the back of the queue. And then, next iteration, I take out 10. 10 is the foremost item in the queue. Right? 10, I will look at my neighbor, 5, 11, 5, 9, and 11. 5 is the source, it's already visited, I don't care. 9 is not, so I will say 9, your predecessor is mine, is 10. You are now visited, and I will enqueue you at the back of my queue. How about the other vertex of the other neighbor of 10, which is 11? 11 is already visited, so I don't do anything. Now, look at this. The usage of queue will allow us to visit 1, 6, 10 first before visiting 0, 2, 9, and 11 later. So 1, 6, 10 are vertices that are direct neighbors of 5. Now, if you follow this one by one, you will realize that the nodes are visited layer by layer. First, you touch all the red one first, the source, and then the green one level above, one hop away from the source, and then the yellow dotted circles. These are the orange dotted circles. These are 2 steps away from the source, and then the black one, black is 3 steps away, and finally vertex 7 is actually 1, 2, 3, 4 steps away. 1, 2, 3, 4, 4 steps away. When the queue is empty, that's the sign for my vertices to stop. When the queue is empty, all neighbors of all vertices reachable from 5, from the source, has been explored. And the predecessor information will form what we call as vertices spanning tree when this vertices is started from vertex 5. Spanning tree. So, if, for example, if I have one to think about, if I have another vertex 13 that is not connected to the main to this component, if I start vertices from 5, I will never be able to touch vertex 13. I will never be able to do that. So, you can play with that in this link. So you don't have to remember URL. You can always go to the main page, Stephen Hub visualization, and then select graph traversal breadth and depth first. When you select this, you have this, right? And then the picture just now is this one. Okay. So if I run breadth first search, if I start from vertex 5, this is the behavior that I'm going to see. Same behavior. From inside going out. From 5 and then 1 layer, 2 steps away, 3 steps away until I visit everything else. And by the way, the vertex numbering is slightly different, so the number are slightly different. The beauty of this tool is that you can now explore your understanding if I start from another vertex. So suppose I start from 12. The vertices behave this way now. Different. It's automatic. It's not scripted. There is an algorithm behind the actual vertices algorithm that computes the whole thing on the fly. Okay. And even if you you can build your own graph. This. Okay. If I run vertices from vertex 1, for example, then immediately 0, 4, 5, 2 will be explored because layer 1, and then 3 will be the next layer. So you can really test your understanding using this script. Right? This is a static example, one example only, but there is no one limiting you to try as many examples as you can from here. Right, now analysis. The time complexity of vertices is phi plus e. So this is the code for vertices, right? The pseudo code. The time complexity is P plus E. Why? Okay, each vertex is only in the queue once because of the presence of Boolean variable visited. If already visited, you will not touch it anymore. You will not put that vertex inside a queue anymore. So it is true that every vertex will only be in the queue once, but there are at least OV component inside already, right? Where's the E? Now look at this. Every time a vertex is dequeued, all its k neighbors are explored, are scanned. Now, if every vertex only touch one, if every vertex explore all its neighbors, another vertex explore all its neighbors, when breadth first stops, means that all E edges have been examined. Like checking the neighbors of adjacency list. This will only work if we use adjacency list, because for this behavior to be OE in overall, you need for every vertex, when you want to scan all its neighbors, you need to be able to do it in OK. If you for every vertex you need OV to enumerate your neighbors. If you do it for all V vertex, for all V vertices, it becomes V times V or V squared. But if we use adjacency list, for every vertex, sometimes we have zero edges, sometimes we have one edge, sometimes we have few edges, sometimes we have 3 edges. But we sum all this together, this sum is actually E, number of edges, the actual number of edges in our graph. So that is the E component. So the time complexity is V plus E. Okay. V plus E. Right. So I will continue briefly to depth first, and I will stop there. And this is just a brief explanation. Next week I will restart from depth first explanation. I want to compare breadth and depth. What is so different? Why is the main difference between these two? See that for depth first, it has some other usage. Some other usage that for now, not many of you probably have seen it before. Right. Again, up to theoretical, not implementation level. So depth first search is another way of looking at traversing graph, but the key ideas is the same, right? But the depth first search visits the vertices in depth first manner. The analogy will be exiting a maze like this, right? Exiting a maze. We will use a stack or implicit stack inside recursion. We still use visited, and we still use predecessor array. So the main difference is instead of going breadth, we use depth. I will show you the behavior of depth first search on 3 here, so that you can really see how depth first search works. So it will go down until you cannot do anything else, and backtrack down, and explore very depth before moving to the next branch. Right? Something like that. So you can compare depth first with breadth first with these two. Okay. We will stop here. Next week we will continue with depth first and application of those graph traversal algorithms.